Good morning, everyone. Myself, Dr. Ramesh Srivastava, Professor, CSE Department, SIRT, Bhopal. So today we will be starting the Module 2, Lecture 2. So in this lecture, we will be discussing swapping, multiple partitioning scheme, external and internal fragmentation. Might be, if the time is left, then paging scheme introduction. So first of all, what is swapping? A process can be swapped temporarily out of memory to a backing store and then brought back into memory for a continued execution. So why we do this? We do this like suppose this is our process loaded into the main memory. Now we can partially swap it out, and then after some time we can swap it again back into the main memory. So when we transfer the process from the main memory to the hard disk, then it is known as swap out or roll out. And when we again bring back that process back into the main memory, then we say that it is swap in or roll in. So why we do it? For better management of memory, so that in the less user space, we can handle or manage more number of processes. So this is why we use the swapping. So in swapping, let us see what will be the total time we will require for swapping out the process and swapping in. So the context switch time in such a system is fairly high. Let us say the user process is of size 10 MB and the transfer speed of the hard disk is 40 MB per second. There are two types of time known as rotational latency time and the head seek time that I have already discussed in the module 1 when we are discussing the disk scheduling algorithms. So the total time, that is the head seek and rotational latency, let us say it is 8 milliseconds. So what will be the swap out time for this particular process? So transfer time will be 10 MB is my user process size, and the transfer speed of the hard disk is 40 MB per second. So 10 for transferring 10 MB, it will require 10 upon 40 seconds, that is 1/4 of a second or 250 milliseconds. So swap out time will be rotational latency time, head seek time plus transfer time. So head seek time we are ignoring, and latency time is given to be 8 milliseconds. So total time required will be transfer time plus latency time, that is 250 plus 8, that is 258 milliseconds. So the same time will be required for swapping in the process also. So total time required, total swap time will be 516 milliseconds. So if suppose we are using the round robin algorithm, then the CPU will be switching between different processes after certain time interval. So for maintaining the efficiency, the time slice in the round robin algorithm should be much greater than 516 milliseconds, because this total swap time is nothing but the idle time. So the execution time should be much more higher than this 516 milliseconds. So that we have to see, that we have to manage, right? Now, we have already discussed that how we map the logical address into the physical address. So with the help of the relocation register, we do it. But now we have introduced the limit register also for maintaining the safety of the user space. Let us say some process length is say 1000 bytes. So what we will do, whatever logical address will be generated by the CPU, we will first of all check whether it is less than the limit register or not. Limit register will be holding the total size of that particular program. So in our case, let us say it is 1000 bytes. So whatever address is generated by the CPU or by the program, it should be less than 1000. So if it is not less than 1000, then in that case, we will simply trap that address and we will terminate the process, because it may be the malicious program or the virus program. But if it is less than the limit register, then yes, in case of yes, we will simply add the logical address generated by the CPU with the relocation register to get the physical address. So this is the hardware support for relocation limit register. for maintaining the safety of the user space. Now, multiple partitioning allocation. So in multiple partitioning, what we do, we keep multiple processes in our memory at the same time. So in this case, we can see here that we have got three processes, process 2, 8, and 5. Suppose after some time, this process 8 completes its execution. So now it is exited from the main memory. So this free space is available to us. This is known as hole. So block of available memory is known as a hole. Holes of various size are scattered throughout the memory. So when a process arrives, it is allocated memory from the hole large enough to accommodate it. Operating system maintains information about the allocated partitions as well as the free partitions, that is the hole. So after some time, here we can see in this scenario, let us say some process 9 comes. So we have got this hole. We will allocate as much memory required by the process 9 from this hole, and remaining memory again will be left with us as a hole. So again, suppose after some time, again process 10 comes. So from this hole, we will allocate the process 10. So the operating system will be maintaining this allocated partitions as well as the free partitions, that is the hole. So this is what we do in the multiple partition allocation. Now, whenever a new process comes and we have to allocate memory into the to that particular process, then we make use of these three types of algorithms: first fit algorithm, best fit, and worst fit. So first fit algorithm says that allocate the first hole that is large enough to accommodate that user. Let us say the user program size is 2 KB, and we have the operating system will be searching the holes from the very first position. So at first position, let us say I've got 3 KB of hole, and our process size is 2 KB. So the first hole will be allocated to that particular process. This is what we do in the first fit. It means allocate the first hole that is large enough to accommodate that particular new process. In best fit, what we do, we allocate the smallest hole that is large enough for that particular process to be accommodated. Let us say, for example, I've got two different types of holes available in the main memory. Let us say first hole is of size 10 KB and second hole is of size 3 KB. So if the user new user program comes and it is of size 2 KB, so the operating system will be searching all the holes. So first hole is 10 KB, second hole is 3 KB. So 3 KB is large enough to hold the 2 KB new process. Okay. So what it will do, it will allocate the 2 KB 2 KB out of that 3 KB space to the user process, and 1 KB will be left again as a whole. So this is what we do in the best fit. But in best fit, what we have to do, the operating system has to search all the table from the very first till the very last and find the smallest hole which is large enough to accommodate that particular process. This is known as best fit algorithm. In worst fit, we just do the reverse of the best fit. That is, again, here the searching had to be done of the complete list of the holes, and we allocate the largest hole to the user process. Now, what is the logic behind this is if we allocate the largest hole for the new process, then we will be assuming that after allocating the space to the process, we will be left with enough memory which can accommodate another processes also. That is what is the logic behind this worst fit. It means that in best fit, as we have already seen the example, so I've got 10 KB of hole and 3 KB of hole. So a new process comes of 2 KB. So we are allocating 2 KB of 2 KB out of that 3 KB in best fit. So only 1 KB is left. So 1 KB might be a small space to accommodate any kind of process, because normally the process size will be larger than 1 KB. This is what worst fit algorithm thinks. So in worst fit, what we will be doing, we will be allocating 10 KB of the whole to the new user process, that is 2 KB. So out of 10 KB, 2 KB is given to the process, and still we are left with 8 KB. So that leftover space of that whole, that is 8 KB, is large enough to accommodate another user process also. This is what the logic is behind this worst fit. In best fit and worst fit, we have to search the entire set of table, that is all the holes in the table, and then we have to make the decisions. In first fit, this searching is not required. The first hole which we find large enough for accommodating that particular user process will be allocated. So in first fit, the searching time is very less, whereas in best fit and worst fit, the searching time will be much larger, right? Normally, the first fit and best fit are considered to be better efficient than the worst fit algorithm in terms of speed and storage utilization. Okay. Now, there are two types of fragmentation, external and internal fragmentation. Let us see with this example. Suppose this is the different processes or segments which are in the main memory. After some time, so let us say this segment 1 is finished. So it will release 8K of memory. So 8K is free. Now 8K is available as a whole. So in the B figure, figure B, we can see that a new process segment 7 comes and it requires only 5K space. So out of this 8K, we have given 5K and 3K is again left as a whole. After some time, let us say this segment 4 is finished. So 7K will be free and a new process segment 5 comes. It requires only 4K. So out of this 7K, we have given it 4K. So remaining is 3K again as a whole. So now we can see that we have got two holes left in this main memory, 3K, each of 3K size, but they are scattered in the main memory, right? After some time, let us say segment 3 is also finished. So 8K of memory is free and segment 6 comes, it requires 4K. So again, we are left with 4K of space in the main memory. So now here we can see that the total space, free space or the total hole size which we are having in the main memory is 3K plus 4K plus 3K, that is 10K. Now, suppose a new process comes and it requires 7K. So we cannot accommodate that 7K in any of these holes because the total size of these holes is not 7K. So what we have to do, we can shift all the used space at one side and all the free space at another side. Like we can see in figure E, we have shifted all the processes used space at one side and all the free space at one side. So we are now having 10K of space and now we can accommodate a new user process of size 7K. So this technique of shifting the user used space at one side and the free space at another side is known as compaction technique. And this fragmented memory, which we are seeing in this figure D, E, D and C, and also D and C is known as external fragmentation because this is known as external fragmentation because this fragmented memory is not usable until and unless we apply the compaction technique to combine all this free memory at one place, right? So that is why it is known as external fragmentation. So to remove the external fragmentation, we make use of compaction technique. Okay. One more thing, as we have discussed in the previous lecture, that why we have to shift the processes from one place to another place in the physical memory at runtime. So that is the reason. This compaction, for applying this compaction technique, we have to shift the processes from one place to another place in the physical memory at runtime. Okay. So now this is external fragmentation, as we have already discussed. In the left figure, this is the fragmented memory. In the left figure, we can see this is external fragmentation. Now suppose we are having a hole of size 1024 bytes and a process comes which requires a size of 1022 bytes. So what we will do, we will allocate this full 1024 bytes to this process because if we allocate only 1022 bytes, then we are left with only 2 bytes. And this 2 byte hole is normally not enough for holding any kind of process, but it will increase the number of entries in the table of the operating system which it is maintaining. As I already told you, the allocation and the free space are maintained as in the form of a table by the operating system. For this 2 byte, I have to maintain one more entry, and this will increase our searching time in the best fit and first fit algorithm, right? So for avoiding this extra entry of 2 bytes, what we do, we allocate this full 1024 byte hole to the process of size 1022 bytes. It means that this 2 byte will be unused, but it will not be used for any other process. So this unused 2 byte is known as internal fragmentation. Okay. Fine. So now let us discuss the paging scheme. So in paging scheme, what we do, we divide our logical address space and the physical address space into fixed size blocks. These fixed size blocks will be in the power of 2. So typically the page size or the frame size, whatever fixed size blocks are present in the logical space are known as pages, and whatever fixed size blocks are present in the main memory are known as frames. So typically this page size and frame size both will be equal. So this typically the page size or the frame size is between 512 bytes, that is 2 to the power 9, and 8192 bytes. Okay. So this I have already discussed. Divide logical memory into blocks of same size called pages to run a program of size n pages. Okay. So now, if we want to run a program of size n pages, then what we have to do, we have to find n free frames and then load the program. Okay. Set up a page table to translate logical to the physical address. In paging scheme, there will be internal fragmentation, but no external fragmentation. Okay. We will discuss this with the help of a diagram. Fine. So now let us see this address translation scheme. So address generated by the CPU is divided into page number and the page offset. So here we can see that the page number is denoted by P and the page offset is denoted by B. And let us say the total logical address space is 2 to the power m. As we have already discussed that the size logical address space or the physical address space will be in the power of 2. So let us say the total size of the logical address is 2 to the power m, and a page size is, let us say, 2 to the power n. So it simply means that we will require the page offset to be of n bits, and the page number will be of m minus n bits. Why? Because the total logical address space is of 2 to the power m, that is m bits will be required for this complete logical address. So if I am using n bits out of that m bits for the page offset, then the remaining, that is m minus n bits, will be used for the page numbers. Okay, we will see it with the example. Let us say the page size is 2 KB. So and logical address space is 4 MB. So find m, that is the number of bits in the page number, and n, that is the number of bits in the offset. So how do we are going to find it? So we have got the page size of 2 KB. We can write this 2 KB as 2 into 2 to the power 10. That is 2 to the power 11. It means that 11 bits will be required to access any address within the page. That is this offset. So D will be of size 11 bits. Now, total logical address space is 4 MB. So 4 can be written as 2 to the power 2, and 1 MB is nothing but 2 to the power 1. The total logical address space is of 2 to the power 22. That is total bits required to access any address within this logical address space will be handled with the help of these 22 bits. Okay. So it means this M, we see in this figure, this M will be of 22 bits. D we have already calculated, it is of 11 bits. So the remaining, that is 22 minus 11, will be utilized for the page numbers. So what will be the number of bits required for page number? It will be 22 minus 11, that is 11 bits. Now, what will be the total number of pages in this particular logical address space? It will be nothing but, since the P is of 11 bits, so the total number of pages can be, maximum number of pages can be 2 to the power 11 with each page size of 2 KB, right? Okay, now suppose we have got the logical address like page number is 3 and the offset, that is D, within that page number 3 is 28. We have to find the physical address. So let us see with this example what we do, how we translate this logical into physical address. So CPU is generating now the logical address of P equal to 3 and D equal to 28. That is a third number page and 28 address within that third number page. This is my logical address. I have to convert this logical into physical address. So what I'm going to do, this page table is maintained, which is holding the frame numbers for each page numbers which we have got in our logical address space. So what I'm going to do, I have to first of all find this third number page in this page table. When I go to the page number 3, in this entry, what we have what we will find? We will find the base address of the frame. Frame is nothing but the physical address, and page is nothing but the logical address. So whatever, and the page size and the frame size will be equal, right? So page number 3 is loaded in which frame? We will find it from here. Let us say this page number 3 is loaded in this particular frame. So we have got the base address of this frame, that is the physical address. So what we do, this frame number physical address or the base address will be added to the offset. Offset is 28 in our case. So 28 will be added to this base address to get the actual physical address corresponding to this logical address. This is how we translate the logical address into the physical address. Let us again look one more example so it will be more clear to you. Let us say we have got this logical memory and I've got 4 pages in my logical memory, that is my program. And these 4 pages are residing in the physical memory at these places. So we can see here that page number 0 is at frame number 1, right, in the physical memory. So in the page table, what I'm going to do, corresponding to page number 0, I will be writing frame number 1. Page number 1 is at frame 4. So page number 1 is at frame 4. Page number 2 is at frame 3. So page number 2 corresponding frame is 3. And page number 3 is at frame number 7. So corresponding entry will be 7 in our page table. Okay. Now let us again look at more deeper level with this example. You will clearly understand how we translate this logical into the physical. So suppose I've got a page size of 4 bytes. Okay. So this is my 4 pages and I've got 4 bytes in one page. So in first page, A, B, C, D is written. In the next page, E, F, G, H is written and so on. Okay. Now page number 0 is at frame number 5. So frame number 5 is this. So here A, B, C, D is written. Page number 1 is at frame 6. That is E, F, G, H is at frame 6. So E, F, G, H is at frame 6. Right. Page number 2 is at frame 1. That is I, J, K, L is at frame 1. Always start the frame also with 0 and always start the page also with 0. So this is our frame number 0, frame number 1, 2, 3, 4, 5, 6 and 7th frame. Okay. So page number 2 is at frame number 1. So frame number 0, frame number 1. So frame number 1, here we have got IJKL, and in page number 3 is lying at frame number 2. So 0, 1 and 2. Second number frame is MNOP, which is our page number 3. Right? Now, what is the physical address of K? This we have to find out. So let us see. This we have to find that this K is lying at which physical address. So what is the logical address of this K? What will be the logical address which will be generated by the CPU? It is page number 2 and the offset is 0, 1 and 2. Okay, so offset is 2 and page number is 2. Okay, so the logical address which is generated is page number 2, and it is at position 3. That is, the offset is a page. Offset is also 2. Fine. So what we will going to do is we will find this page number 2 in our page table. So page number 2 is indicating that it is lying into the frame number 1. Fine. Okay. So size of the page or frame is 4 bytes. So what I'm going to do is this frame number 1 is multiplied by the size of the frame, that is 1 into 4, plus the offset is 2. Right. So 1 into 4 plus 2, that is 6. So this must be the physical memory address of K. Okay, let us see here. So we can see here that I is at 4th position, J is at 5, and K is at 6th position. So this is how we are converting the logical into the physical address. Let us see one more example. What is the physical address of F? Okay, so physical address of F. So here we can see F is at page number 1, and the offset is also 1. Right? We are starting with it is at position 2. It means the offset is 1. Fine. So page number 1 and offset 1. This we have to do. So page number 1 is at frame number 6. Fine. So what we are going to do? 6 into size of the frame, that is 4. That is 6 into 4, 24. Plus offset is 1. 24 plus 1, 25. So this F must be at 25th position. So we can see here F E is at 24th and F is at 25th position. Right? So this is how we are going to calculate the physical addresses corresponding to the logical addresses in paging scheme. Okay, this is another example how to calculate the logical physical address of the P. So this is the introduction to the paging scheme, and that is all for today. And we will see the next into the next lecture. Okay, thank you.